Okay, good day. This is Math 140 College Algebra. I'm Professor McCulley, and this is the lesson for section 2.6 on variation. Let's get right to it. Today we're going to write direct variation equations from verbal descriptions. We're going to write inverse variation equations from verbal descriptions, write joint variation equations from verbal descriptions, and solve equations. So what are these three things? Well, they're fairly easily defined. Direct variation is a linear model with y-intercept of 0. Y varies directly with x, or y is directly proportional to x, are two key phrases that will let you know that you have a direct variation model. The general direct variation model is y equals kx, where k is the constant of proportionality. And you'll notice I have there in both highlighted and underlined and boldface there, do not forget the constant of proportionality. That seems to always be the biggest problem that kids have when they take these problems. They just make it y equal to x, and they forget their constant of proportionality. Inverse variation, y varies inversely with x, or y is inversely proportional to x, are a couple of expressions that tip you off to the fact that you're doing inverse variation, and the general model is y equals k over x, where k is the constant of proportionality. And again, do not forget the constant of proportionality. A lot of times I'll see when people have y is inversely proportional to x, I'll have a student write y equals 1 over x, and that is wrong. You need that constant of proportionality. Do not forget. Joint variation, z varies directly with x and y. Z is directly proportional to x and y, and that general model would be z equals to kxy, where k is that constant of proportionality. Do not forget your constant of proportionality. Hopefully you're starting to see a pattern here, just as I intended. Here is the process that we're going to use for solving direct variation problems. We're going to determine the type of variation equation. Then we're going to use a given instance to solve for the constant of proportionality. Don't forget that part. That is the hard part. That is the key, and that is also the part that's most often forgotten. We're going to rewrite the variation equation using the constant of proportionality, and we're going to use the new function to make a prediction. So what does that look like? Here is an elementary example. Suppose that y is inversely proportional to x, and x equals 12 when y is equal to 2. So write an equation that models the function. So the first thing we're going to do for part A here, after I get the correct tool, part A, it says y is inversely proportional to x. So y is equal to k over x. That's where I get from inversely proportional to. And if we talk about, we've determined the type of variation, and then we're going to use the instance to solve for the constant proportionality. So what does that mean? They give us this instance right here, x equals 12 and y equals 2. Well, we're going to get a value for k here. And so if I plug in 2 for y and I plug in 12 for x, well, here I'm just going to multiply by 12 and I'll get k equaling to 24. So my final answer for A is y equals 24 over x. That is my model. Then part B says, what is the value of y when x equals to 4? Well, what we're going to do is we're going to plug 4 in for x and solve for y. So y equals to 24 over, let's see, x equals 4. That's going to give us 6. So when x equals 4, y equals 6 is our final answer for that right there. The next one, x varies directly with y and the square of z. If y equals 2 and z equals 3, then x equals 6. Write a model that, write an equation that models the situation. So A, x varies directly with y and the square of z. So z squared. So when I say, let's see here, when y equals 2, z equals 3, x equals 6. So I'm just going to plug in. So I'm going to go 6 for my x. I don't know what k is. y is 2, 3, or z is 3. And so let's see here, let's simplify on this side. I get 3 squared is, 3 squared is 9, times 2 would be 18, is equal to k. Divide both sides by 18. I'll get k equals 6 over 18, which is 1/3. So that's my k. And so my equation is going to be x equals 1/3 y z squared. That is that expression right there. And then part B, what is the value of x when y is equal to 4 and z is equal to 4? Well, I'll have 1/3. I'll have y equal to 4. I'll have z equal to 4. And then I'll be x equals, let's see here, a third times, let's do it in the proper order. 4 squared is 16. 16 squared, or 16 times 4 is 64. 64 times a third is going to be 64/3. And that is going to be my final answer for that particular problem. All right, let's drop down another one here. It says, the weight of a person on Mars varies directly with the weight of a person on Earth. When the weight of a person on Earth is 100 pounds, the weight of the same person will only be 98 pounds on Mars. What would the weight of a person on Mars if they weighed 175 pounds on Earth? Okay, so the weight of a person varies directly with the weight of a person on Earth. So we're just going to go M is weight on Mars, and E equals the weight on Earth, and M equals KE. And so we have an instance right here. So 150 and 98. So when a person is 98 pounds on Mars, they weigh 150 pounds on Earth. So K equals 98 over 150. Let's use our graphing calculator to reduce that particular, let's close, 98 divided by, oops, not that, 150. Let's hit math, let's hit fraction, let's reduce that. So 49/75, so not much reduction there. 49/75. So my equation is going to be M equals 49/75 E. And so if they weigh 175 pounds on Earth, we want to know what they weigh on Mars. So the Mars weight will be 49/75 times 175. And so I'm just going to grab my graphing calculator since I already have that as my answer. Just hit multiply to get the answer up there, 175. And, ooh, I would rather have that be a decimal here. So 343 divided by 3 equals, so 114 and a third of a pound. So we'll go, the Mars weight would be 114.33 pounds. Okay, last example. The volume of a given amount of nitrogen is inversely proportional to the pressure of the gas in the container and directly proportional to the temperature. If the volume of a given amount of nitrogen is 2 cubic meters when the pressure is 2 atmospheres and the temperature is 10 degrees Celsius, what is the volume of the given amount of nitrogen if the pressure is 3 atmospheres and the temperature is 15 degrees Celsius? Okay, so let's start going through the stuff. Let's call V the volume, and we'll call it in meters cubed. And P is the pressure, P-R-E-S-S-U-R-E, in atmospheres. And T is the temperature in degrees Celsius. Okay. So the volume V is inversely proportional to the pressure P and directly proportional to the temperature T. All right, and since we have written it this way. This K is going to end up being a constant proportionality that relates to nitrogen only. And so um, even if everything else remains the same, where volume is inversely proportional to the pressure and directly proportional to the temperature, it's going to depend on what type of gas you use in each particular instance. So let's plug in what we got. It says 2 cubic centimeters our cubic meters of nitrogen. So 2 equals to K when the pressure is 2 atmospheres and 10. So I can reduce this and we'll make it 2 equals 5K. That means K will equal 2 over 5. All right. And so our new equation V equals 2/5 T over P, and I assume that we could simplify that further, but this isn't asking for a equation. It's just asking for us to figure out what the values are. And so what I'm going to do is I'm going to say, it says, what is the volume? That's what I'm looking for. So V is what I'm looking for. The pressure is 3 atmospheres, so 2 over 5. We'll put a 3 in for P, and then we'll put a 15 in for T, and let's see if we can simplify that ourselves. Let's see here. I'll get 2, um, let's see here, 15 times, or excuse me, 2/5 times 15. Well, I can cancel out a 5 there and give me a 3. And then 2 times 3 will be 6. I'll get 6 over 3. 6 over 3 is also 2. And so we'll call this 2, let's see, meters cubed. Now, what you're going to say is, hey, wait a second, Mr. McCulley. Didn't we just say that it was a nitrogen of 2 cubic centimeters and the pressure was 2 and the degrees, the Celsius was 10 degrees? Well, yes, we did. But remember, as the volume or as the temperature goes up, the volume goes up. As the pressure goes up, the volume goes down because it's inversely proportional. So what happened here is the temperature went up enough to compensate for the increase in pressure. And so the temperature goes up, the volume goes up, the pressure goes up, the volume goes down. It worked each other out, and that's how we got that final answer. So that's all I've got for today, folks. So today's Marvel fun fact of the day: Tom Holland has claimed that the main inspiration for his take on the characters of Spider-Man is Marty McFly from Back to the Future. That's all I've got for today, folks. Have a good day. Goodbye.